In this video, we're going to have a look at oxidation numbers. So we're going to look at why some elements have fixed oxidation numbers and how it relates to the structure and the bonding in the type of elements and compounds that we're forming, and see if that helps to make a little bit more sense about why there are some fixed rules for oxidation numbers and why there are some exceptions to those rules. So the rules we should already know is that there are some elements that have fixed oxidation numbers. For example, group 1, group 2 and group 3 would always be +1, +2 and +3 respectively. Fluorine, we should know that fluorine in a compound is always -1 without exception, and that oxygen is usually -2, but then there are some exceptions that we need to know, and hydrogen is usually +1. And again, there is an exception to the hydrogen rule. But actually, all of these exceptions can be easily explained by just looking at the type of bonding in the compounds with exceptions. So group 1, 2 and 3 are metals. They have very low electronegativity values, which means they do not attract electrons to them very effectively. And on the left-hand side of the periodic table, which means they have a relatively low number of protons compared to the shells of electrons that they've got. So they don't have a good hold on electrons, don't have a strong nuclear attraction. So for that reason, they're almost always going to form ionic compounds. And for that reason, they're going to form ions with fixed charges. The reason they form ions with fixed charges is related to ionization energies, not full outer shells. We're not going to go into that right now. But there are a couple of what we might consider metals, such as beryllium, that actually although they have a low electronegativity, they have a high enough ability to attract electrons that they actually form covalent compounds. So beryllium chloride has come up before in shapes of molecules because it's a linear molecule with 2 chlorines attached. There can only be 2 chlorines because beryllium is in group 2, so it only has 2 electrons in its outer shell. It doesn't form an ionic compound with chlorine because if you imagine that beryllium were to lose those 2 outer electrons, it's going to end up with a very, very positive, a 2+ ion with just 2 electrons. So it's got 4 protons and 2 electrons. So it has a very strong attraction to electrons, and therefore it does end up forming covalent bonds. However, it's still a polar covalent bond, and so we can think of beryllium as having a +2 charge because it forms 2 covalent bonds in which it is the more positive of a polar covalent bond. Similarly, we looked at aluminium trichloride when we were doing our bonding questions, and we know that it also forms a covalent molecule for the same reason, so that when aluminium loses 3 electrons, it actually makes a very, very densely positively charged ion, which actually has an ability to attract the electrons back from the chlorine and form a covalent bond, but a polar covalent bond. So even when metals are covalent bonding, they're still going to be the least electronegative element in that bond. And if we are to count aluminium there, it made 3 bonds, which give it, and it's still a 3+. So we can look at the number of bonds as well as the ions that it would form. What about fluorine? Why is it always -1? There are no exceptions to that. So fluorine can form an ionic compound with metals, such as sodium, and there's no give in the way that it forms ionic compounds. So fluorine is in the second row of the periodic table. So these 7 electrons are in the second shell. The maximum that we can hold there is 8 because we only have an s orbital and 3 p orbitals. So the maximum that fluorine can do in terms of forming a negative ion is simply to gain 1 electron. There's no give or take there. What it also means is that fluorine can only form 1 covalent bond. The halogens have other options. Lower down the group, they can form more than 1 covalent bond. Fluorine can only form 1 for this reason of it being in the first the second shell, and only being able to hold 8. So, and when fluorine forms bonds with any other element, it is always the most electronegative. So fluorine is the most electronegative element on the periodic table, unless we were to count noble gases, which we don't, because the definition of electronegativity is to withdraw electrons from covalent bonds. The next noble gas from fluorine doesn't make any covalent bonds, so we can't measure its electronegativity. So fluorine is the most electronegative element, and so even if it were to bond with a relatively electronegative element such as nitrogen, fluorine would end up -1, and in this example, nitrogen would end up with a +3. So the reason it only is -1 is because it can only form a -1 ion, or it can only form a single bond to other elements which are less electronegative. Oxidation number can sort of be thought of as either the charge that the ion actually has, if it's an ion, or what charge would form if the covalent bond were to break. What charge would that element end up? Would it take the electrons with it, or would it leave them behind? So let's have a look at oxygen, and hopefully you're now starting to see a trend, because we said that oxygen is usually -2. And that there's a couple of exceptions, but most of the time it is -2. So oxygen's also in the second row of the periodic table, which means that when it forms an ion with metals, it will absolutely only form a 2- ion. And so it definitely has a fixed oxidation state when it comes to forming ions. And in a typical compound with other elements that are covalent, then you can see that oxygen will normally form 2 bonds. In fact, it can't form any more than 2 bonds, again, because it's in that second period of the periodic table. We're talking about a shell that only has a maximum of 8 electrons, only 3 p orbitals and 1 s orbital. So, for example, if oxygen were to bond with hydrogen, hydrogen is less electronegative, oxygen is more electronegative, and it forms 2 bonds. So we therefore end up with 2 pluses. So counting the polarity of both the bonds it's forming, if it were to break both of those bonds, it would end up pulling the electrons with it and being a -2. Let's have a look at one of the exceptions where oxygen is not -2. So that would be in OF2, and that would be called oxygen difluoride, excuse me, which is interesting because normally oxygen goes at the end of a name, such as sodium oxide, sulfur dioxide, nitrogen dioxide. These are all clues, by the way, so when an element appears at the end of the compound, it means it is the most electronegative one. We always write our formulae in order of least to most electronegative, and we do the same for our naming. So OF2 would actually be called oxygen difluoride, not difluorine oxide. So, oxygen bonding to fluorine, fluorine remains the most electronegative. So fluorine has to be -1, which means oxygen has to be +2 in order to balance the oxidation states. Other way of looking at that is if we were to break those covalent bonds, the fluorine would be the one that ends up with the electrons, and the oxygen would lose both of those electrons. So we're imagining what would happen if we broke the bond and ions were to form. Another example where oxygen is not -2 is in a peroxide. So hydrogen peroxide is the most common that can happen here. And again, we're thinking about the bonding. What would that look like? Well, if oxygen needs to form 2 bonds and hydrogen forms 1, that would be how we would draw hydrogen peroxide. The hydrogen-oxygen bonds are polar because hydrogen is less electronegative than oxygen. But the oxygen-oxygen bond is not polar because there's obviously no electronegativity difference between the 2 oxygens. If we now look at how we've written our delta minus, each oxygen only has 1 delta minus on it. So it's only forming 1 polar bond instead of 2, so it becomes -1. Hydrogen, we have another rule for hydrogen, and we say that it's normally +1. There are very few times when hydrogen is not +1. So the reason for that, hopefully we're starting to see a trend here, is that hydrogen has a very low electronegativity. It's one of the least electronegative of the non-metals. And so that would mean that hydrogen almost always forms, well, when it's forming a covalent bond, it will always form a delta positive. It can only form one bond. The other option for hydrogen, though, is that it can react with metals. And if it reacts with metals, then obviously the metal would be the least electronegative. And it would form a negative ion, and that would be called a hydride ion. So again, we have clues in our naming, because H+, the ion that we're more used to hydrogen forming, we're more used to hydrogen forming an H+, because it's normally bonded to something like oxygen. Oxygen is more electronegative, so when that bond breaks, we release H+. We don't change the name of H+, we call it hydrogen ion, in the same way that we don't change the name of a sodium ion, a potassium ion, or anything else that has a positive charge. Incidentally, ammonium has that ending because it's a positive ion, so it has an ending -ium to make it in line with metal elements to show that it has a positive charge. So hydride has a negative charge, so the only time that hydrogen cannot be +1 is when it is with a less electronegative element, such as a metal. Aluminium hydride you will come up with in organic chemistry. Halogens come up a lot in redox, and it seems like they have an almost unlimited range of oxidation states, but actually the rules are again related to the bonding. So if you put a halogen with a metal or hydrogen, the halogen will be more electronegative, and with a metal, of course, the halogen will be forming a halide ion, and so we'll definitely have a -1 charge. With hydrogen, then we're going to find things like hydrogen halides, which are covalent compounds. Hydrogen can, of course, only form one bond with the halogen, and so you're going to end up again with a polar molecule where the halogen is the more negative, is the one that is more electronegative, forming one bond. So this is why we get -1. But then there are options where halogens can bond with other elements, and in particular where you get variable oxidation numbers is where non-metal elements are bonding with oxygen. And so there are options now, and it turns out that we're going to be making something called halate ions. So halogens don't really bond with oxygen to form neutral molecules, they bond to form negative ions. Another wording on 8 always means negative as well. Okay, so there are no 8 ions that have positive charges. And if I write the formula here for the 4 possible halate ions that chlorine can form, we might be able to see some trends. So halate ions are always negatively charged, and you can see that basically these always have a -1 charge as well, and that they increase in their number of oxygens by 1 each time. And that this is the maximum possibilities that chlorine can have. Bromine can do the same, iodine can do the same. The reason they can do all of this is because they can form more than one bond, unlike fluorine, because they are now in the 3rd shell and below. So we're now talking about possibility of up to 18 electrons. So how we name these ions? This first one would be chlorate 1, and that's because if the oxygen is -2, which we know that it has to be, then chlorine would be +1. The oxygen is -2 because it's more electronegative than chlorine, so it follows the normal rules, and it's going to be making 2 bonds with the chlorine. So this would be chlorate 3. The next one, starting to see a trend now, would be chlorate 5, and the final one would be chlorate 7. So each time you're adding an oxygen has an oxidation number of -2, so the chlorine is going up by +2 each time in its oxidation number. So there are no even-numbered oxidation states in these chlorate ions, and that's because you'd be adding the oxygens together and we'd end up with an uncharged molecule. Chlorate 7 is the maximum that we can make, and that's because 7 bonds is the maximum that chlorine can make with oxygen, and that's because it's in group 7, so it only has 7 electrons to share, which means it can only possibly increase its oxidation state up to a maximum of +7. And all the other halogens will do this except for fluorine. Fluorine won't do it because it does not have space in its outer shell. If we were to draw the bonding, you could see that 3 of the oxygens would be forming double bonds with the chlorine. So that's 6 bonds in total. And then the final oxygen would only be able to form a single bond because we've only got 1 electron left in our chlorine outer shell. And that's why that oxygen would have to have a negative charge in order for that oxygen to have 8 in its outer shell. And oxygen does really have 8 in its outer shell, every compound. I know we've done some exceptions. Oxygen is a bit of a stickler for having a full outer shell. So that's the maximum we can have. And as I said, iodine and bromine could do the same thing. So +7 is the maximum, -1 is the minimum because that's the most negative ion that we can form. There's lots of different trends in oxidation numbers that we can see in the periodic table related to their position and their group. Transition metals, ever since GCSE we've been told that they can have more than 1 oxidation number in a compound, and you will be looking more at this and into a whole topic on transition metals in the second year of chemistry. So if we were to look at the full electron configuration of iron, we've got all our inner shells which are full, and then our outer shell is a combination of 4s and 3d. And there are 2 in the 4s and 6 in the 3d. And if we think of our electrons in boxes, our model for showing electron orbitals, then altogether you've got 6 orbitals there. You've got a 4s which has 2 electrons in it, and in a 3d you would put in your 5 electrons and then just 1 of the electrons would be paired. So that's the iron atom. And we know that iron can form a 2+ charge, as can the majority of transition metals, and it forms a stable 2+ ion by losing the 4s electrons. So remember, we fill the 4s first, we take away from the 4s first as well. If we were to compare that with the other common oxidation state of iron, which is Fe3+, then what you end up with is a beautifully unpaired, a kind of half-filled d orbital in which all of the electrons are unpaired, and that happens to be a particularly stable oxidation state. So 3+ actually tends to be usually the maximum positive charge that we can get simply by losing electrons. So any times that you see transition metals with much higher oxidation states, such as 6 or 7, we're actually not looking at losing 6 or 7 electrons. That would be a ridiculous amount of ionization energy. What is actually happening in transition metals that have oxidation states of +6, +7, or perhaps +5 is the same as what is happening with our halogens when they have high oxidation states. They're not genuinely losing that many electrons. So this one would be manganate 7, because my 4 lots of oxygen give me an oxidation of -8. The whole thing has a -1 charge, so the manganese has a +7 state. Looking at the trends, we're naming these the same as we're naming the halate ions, so we've got 8 at the end, meaning it's negative. Chromate 6, and that's because, again, if you look at the charges and add them up, chromium is the one with the oxidation number of 6. And they are doing exactly the same sort of thing that the halogens are doing. So manganese in manganate 7 is forming 7 bonds with my oxygen, and then the remaining oxygen ends up with a minus charge. That's going to be the maximum oxidation state for manganate, and that is because if you look at where manganese is in the periodic table, it's 4s2 3d5, which means it has a total of 7 electrons that it can share with our oxygen. Manganate 7 is a really good oxidizing agent. Generally, transition metal ions that are in their most positive oxidation state are going to be good oxidizing agents. Chromate 6, I didn't draw dichromate because it's a bit more complicated. It's really similar in structure to just sulfate ions. Again, you've got 6 bonds and then 2 of the oxygens have negative charges. Incidentally, this also leads to a rule that's quite handy when you're trying to remember the charge, whether the charge on an 8 ion is -1 or -2. So if we looked at our halate ions, chlorate, bromate, iodate, they all had a -1 charge. And they were all in group 7, so they had an odd number in their group, an odd number in their maximum oxidation state. And they had an odd charge, -1. Manganate's the same, so manganate 7 has an odd charge, -1. Chromate 6 has an even number oxidation state, even numbered charge. It's just to do with the way that oxygen bonds, because it always forms 2 bonds or 1 bond and a minus charge. And then there are some trends that can help us with the common ions that we see that we don't give oxidation numbers to because they are so common. We don't tend to give the proper names to carbonate, nitrate and sulfate. They're just ones we had to learn at GCSE. So carbon's in group 4. So the carbonate ion, it's forming 4 bonds with the oxygen and it's got an oxidation state of +4 because of that. We can add it up. It has a 2- charge, and that's because 2 of my oxygens need negative charges because they're only forming single bonds. The oxygens each contribute to -2 in the oxidation number, so the carbon must add up to +4. So the proper name for that ion would be carbonate 4, but we don't call it that because actually it's the only stable form that carbon can form with oxygen other than carbon dioxide. Nitrate's a bit confusing. So nitrate is in group 5, nitrogen is in group 5, but it can't actually form 5 bonds because it's only in the second row of the periodic table. So it can't have more than 8 in its outer shell. But it can bond with 3 oxygens if it forms a double bond with one, a single bond with another, and then uses its lone pair to make a dative bond to the 3rd electron. So why would it do this? Well, remember, forming bonds gives out energy. So elements are going to tend towards the maximum oxidation state they can have if they're bonding with oxygen, because forming a bond with oxygen releases energy. And so the common form of each group, you'll notice, is the highest oxidation state that it can be. Also notice it has a -1 charge because it's in an odd numbered group. If we were to look at sulfate, then the proper name for this ion would be sulfate 6. 6 bonds to oxygen. We have a 2- charge because we have 2 oxygens that both require a negative charge to fill their outer shells, and we call it sulfate 6. So there are other examples of sulfate ions. There's SO3, 2-, which should be called sulfate 4, but is often called sulfite. And if you do biology and you do the nitrogen cycle, you will have heard of nitrates and nitrites, which are really just both nitrate ions, but with differing oxidation states, so differing numbers of oxygen that can bond all together. We're just going to finish off looking at some unusual oxidation numbers and how they arise, because they can throw people off as well. So if we look at this unusual little formula, this wouldn't be used much except for maybe in a multiple choice question, just to try and work out the oxidation states. So sodium is fixed, +1, so the total from the sodium is +2. Oxygen, in this case, is not bonded to fluorine or itself, so we're going to keep it at -2, so it contributes to -12, which means my 4 sulfurs must add up to a total oxidation number of +10. So how can that happen? Because what that means, of course, is that the average oxidation number, if we were trying to write the oxidation number per sulfur atom, would be 2.5. which a lot of students don't like. And justly so, because you can't lose half an electron and you can't form half a bond. So none of these explanations so far have explained how an element can work out with an oxidation number of 2.5. So let's just look at the iron on its own without the sodium, because the sodium is ionically bonded and not really covalently bonded to it. It makes a lot more sense if we actually draw out what this iron is. So there's a sulfur bridge in the middle. Sulfur bridges are fairly common again. If you do biology, you've seen them in enzymes. And sulfur does form chains. So sulfur can form 2 bonds, just like oxygen can. It's in group 6. Or if we look at the sulfurs on either end, those sulfurs are forming 6 bonds to these 5 to the oxygens and 1 to the sulfur. If we were to consider then individual oxidation states using this idea of how many polar bonds are they making, well, the sulfurs in the middle is essentially the same as elemental sulfur. There's no polarity in those bonds because sulfur has the same electronegativity as sulfur. So those 2 sulfurs in the middle are essentially oxidation state 0. They don't have any polarity. The sulfurs on the end, each forming 5 bonds with more electronegative elements with oxygen. And so each sulfur on either side can be thought of as being a +5 oxidation state. So in total, amongst 4 sulfurs, the total number of bonds to more electronegative elements is going to be 5, and therefore the total oxidation state is +10. But of course, some of the sulfurs are 0 and 2 of the sulfurs are +5. So this is where we get unusual oxidation numbers instead.